Hi, this is Tzvi Rosen. In this video, we'll be discussing how to construct a regular pentagon. This is the task that I owe you from the first lecture, which I left off because it ends up being quite complicated. So let's start off with an important supporting point. First of all, the sum of the angles in a convex N-Gon. Okay, so let's say we have, let's start with, some n points. Okay, let's make it 6 so we're not boring. So when we connect these points into an N-Gon, and we make sure that there's no corners bent in, like the shape is convex, so we can add a point anywhere in the middle and then connect everything with lines to the center. Okay, and what results is a triangle for every one of the edges of the N-Gons. There are n triangles here. Oops. And so if I wanted to add up all of the angles in this picture, okay, so I'll go, let's start adding things up. And I would notice that, well, in each triangle, has 180 degrees, and there are n triangles. So the total angles, or the sum of the angles, is 180 times n. But if we count this differently, looking at the corners, the sum of the angles is also given by the sum of angles in the N-Gon plus 360 degrees from the center. Okay? And so what does that mean for us? It means that (180 times n) is equal to the sum of the angles in an N-Gon plus 360. Okay? And if I want to solve for this, okay, so sum of the angles in the N-Gon, that's going to be 180n minus 360, or if I want to factor out 180, that gives us 180 times n minus 2. Okay? Of course, if you want to do this in radians, this would just be pi times n minus 2. Okay. Cool. So what does that mean for a regular pentagon? So let's draw a circle. Okay, and we can draw some points approximately evenly spaced around here. So we have, let's make this cool. Yeah, trying for evenly spaced is really a fool's errand unless we use constructions with compass and straight edge like we will in GeoGebra. But let's continue this way. So if you're approximately evenly spacing these, okay. Okay, so what does one of these angles look like? Okay, well, we know that the sum of the angles is equal to 180 times 5 minus 3, sorry, 5 minus 2, which is 540. Okay, and we know that in a regular N-Gon, all of the angles are equal. So in regular pentagon, all 5 angles are equal. So x equals 540 divided by 5, or 108. Okay, so each of these angles is 108 degrees. Okay. And how does the 36, 72, 72 triangle come into this? Well, let's grab this. We are going to try to we're going to add in some diagonals to this picture and see what insight that lends. Okay, so let's add in a diagonal here, and here, and here, and here, and here. Okay. So my claim is that this is a 36, 72, 72 triangle. Okay. And those numbers might not mean anything to you, but the fact that's important is that the two larger angles are twice the smaller angle, right? And they add up to 180. So how do we know that this is 36, 72, 72? Well, let's mark this as, let's call that x, and we'll call this y. Well, we know that this also would have to be equal to y by symmetry. Okay, and then by the same token, you could go around labeling all of these y and all of these x. But then you could use symmetry to observe that the central pentagon, so the pentagon formed by the diagonals, is also a regular pentagon. Okay. And when we notice that, that tells us that, let's give this a new color. Let's give it orange. Okay, so this angle is 108. But we know by our principles regarding intersecting lines that this is also 108. But then we know that 2y plus 108 must be equal to 180. And that tells us that y is going to be 36. Okay. And we know that x plus 2y is equal to the entire angle of this pentagon. So that tells me it's 108. We know y is 36. This is 72. And that tells me that x is also 36. So all of the angles, so x and y are 36, and that tells me that this angle is 36, and then x and y together are 72. So this is 72, and this is 72. So we have a 36, 72, 72 triangle. Okay? And so that's going to hold the key to building a regular pentagon in a circle. You'll start with the 36, 72, 72 triangle, and then once you know that this is a side of your pentagon, this line segment here, then you just draw a circle and you get it over here. And by the same token, over there, and then you've got all 5 points and you're done. Okay, so we need this 36, 72, 72 triangle, and part of finding that is using the golden ratio. And now let's grab this. Let's see if we can, how much of this triangle we can get. Okay, that's not bad. Okay. So this is our 36, 72, 72 triangle. something to observe about it. Oops. Something to observe about it is if I bisect either of the larger angles. So for example, let's do that with this angle. Oops. So let's say we're bisecting it. Now, since we're cutting that angle in half, this is 36, and we know this angle is still 72, this angle. And then this angle will also be 72 because it has to add up to 180. So this smaller triangle is similar to the larger triangle. Okay. And let's say we are going to call this length x. So let's say that how do we want to do this? Let's label this as 1 and this as x. Then this also has to be 1 because this guy, the small triangle, is an isosceles triangle. Okay, so far so good. But then we know that this is also 36. So we have 36 on either side here. So that means that the top triangle, this one, okay, that's also isosceles. So this length also has to be equal to 1, which means that this is 1 plus x. Okay. And if we are trying to solve for x, then what we're going to find is 1 plus, so the way we'll do that is by using the ratio in the triangle. So I know that the longer edge to the shorter edge has to be equal to, for the two triangles. So we'll have 1 plus x divided by 1 has to be equal to 1 divided by x. Okay, and that tells me that 1 plus x times x equals 1. X squared plus x minus 1 equals 0. Okay, and the solution to this is -1 plus or minus the square root of b squared minus 4ac is 1 plus 4 divided by 2. This gives us -1 plus or minus the square root of 5 over 2. Okay, so we know x is a positive length, so we're not going to take the negative root. So this we deduce is going to be √5 minus 1 over 2. Okay, and if I want to know the length of this full side, that's going to be equal to 1 plus √5 minus 1 over 2, which is the same as 1 plus the square root of 5 over 2. And that is the golden mean, also known as phi. Okay, so that's why, or the golden ratio. And that's why the golden ratio comes up in our computations for a regular pentagon. And you probably, you might have considered this already in preparation of your journal assignment. But that's also going to come up in our construction, which is based on Euclid's construction of the regular pentagon. And now we'll switch to GeoGebra to illustrate the full proof. Okay, so here we present Euclid's proof of how to construct a regular pentagon, and it's based on constructing the 36, 72, 72 triangle, and here is the breakdown. First, you construct a segment of length phi, the golden ratio. And then you use this to construct a 36, 72, 72 triangle. Then you inscribe the triangle in a circle. and you add in the remaining 2 vertices and connect the dots. Okay, so let's start with constructing the golden ratio. Okay, so first you draw a square ABFG. Okay, and drawing a square is as simple as drawing perpendicular lines and then using circles to make sure the sides are equal. And then you label the midpoint of one of the sides of the square. So in this one we labeled J, the midpoint of side AF. I wish the font was bigger here. Let's see if I can make it bigger. Okay, in any case. So once you construct that midpoint, you send it down to the point. So to get the point K down here, you draw this pink circle so that the one radius is the segment JB. Okay, so it's from this midpoint to a corner opposite, and you draw a circle centered at J of that radius, and where that intersects the line that J is on, that J forms with A, you mark the point K, and you can swing that radius up to get a segment AL of length given by so that the length the ratio of the length AB to the length AL is the golden ratio. Okay. To persuade yourself that this construction works, I've written out a proof here, and the idea is just to show that that the ratio in question satisfies the polynomial relation x squared equals x plus 1, which the golden mean satisfies. And it's relatively simple, just applying the Pythagorean theorem and figuring out which lengths are equal to what. But once you finish up, you see that this ratio is indeed equal to the golden mean. Okay, so we have a segment with a subsegment, so that the ratio of the larger to the smaller is the golden mean. Okay, and we're going to use that in the next page to construct a 36, 72, 72 right triangle. Okay, so first up, we draw our line segment ABC, so that, and let's see if we can find it. It was this segment this segment between points A and B, with a point C such that AB over AC is the golden ratio. So if we're looking at this, a little bigger. Oh, here we go. So if we're looking at the ratio of AB to AC, that's given by the golden ratio. Okay, so that's what we start with, and we know we can do that based on the previous page. Then we draw a circle centered at A with radius AB. Okay, and then you draw a circle N centered at B with radius AC. And then you mark an intersection point of M and N, those two circles, as your point D. And where is that? I think we mark that as I in this version. And the circle the triangle ABI, or ABD in the description above, is a 36, 72, 72 triangle. Okay, and I've written out the proof here as well. It relies on a few facts about circles, which are probably outside of the scope of this video, but which you can consult on this GeoGebra book, which I will be posting with the YouTube description. Okay, and so we know now how to build a 36, 72, 72 triangle. And now, given that ability to build a 36, 72, 72 triangle, we have the following steps. You make your 36, 72, 72 triangle, and then you can inscribe it in a circle. And this is something you're always able to do with a triangle. You're able to find a circle that passes through these 3 points. And there's a method in Euclid for how to do that as well. Then you draw a circle centered at B with length B. So we have our oops. So we have our 36, 72, 72 triangle. So we draw a circle. Let's find the appropriate circle. So we have a circle centered at B through J, which we use to build the circle, the other intersection point K. Okay, so now we know that the length of BJ is also equal to the length of BK, and then we do the same on the other side. We get it's this circle. And then we get this circle to confirm that KA is equal to KB. And then we can get the remaining point by drawing a circle centered at A. Equivalently, we could have drawn a circle centered at J. And we see that we have 5 equally spaced points around the circle, and that gives us a pentagon, a regular pentagon. And we've marked off the lengths here, and as I drag around this point, you can see that the lengths are all changing together. And we always have the same lengths for the sides of the pentagon. Okay, and that gives us our regular pentagon, and hopefully you don't feel like I've left you hanging from last lecture. And to see more details of those proofs, I'm going to post the GeoGebra book link, and you can see the writing there. Okay, thanks for your attention.